Okay, well, in this last video, we're going to go ahead and cover several example problems. So let's get to it. So this problem reads, in an effort to save energy, it is proposed to change the standard frame wall construction with half-inch gypsum board and half-inch plywood with a 1 by 8 inch wood drop siding from 2 by 4 studs and 16-inch centers to 2 by 6 studs at 16-inch centers. Wants you to make a table similar to that in your book, table 5.4a, showing both of these constructions using 5.5 and 3.5 inch fibrous glass insulation. And wants you to compare the two constructions, assuming winter conditions. So basically what it's saying is you have one wall that is made by 2 by 4 studs, and another one is made by 2 by 6 studs. Intuitively, we would think that the 2 by 6 studs would have greater insulation than the one with 2 by 4, but we're going to go ahead and quantify that. So let's set up a table similar to what we did in the prior example problem. So again, that would be, we would have material followed by thickness, conductivity, density. Those are the properties that we would extract from the tables within the chapter. Now, understand that the difference between this example problem and the last example problem is that in this one we're going to have some materials aligned in parallel, right? So if you have this as one stud here and this is another stud here, in between is going to be insulation. So what I'm going to do is treat this problem as if we're having one heat flow in series going through the stud and another heat flow in series going through the insulation. And what that does is that it allows you to look at two basic paths that the heat flow would go through. So the total resistance on the stud side and then total resistance going through the insulation. So what I mean is on the stud side, you would have as a first heat transfer mode, you would have convection through the outside air. And then you would have conduction through the siding, then through the plywood. Then the heat flow would either go through the insulation or the stud. And then from there, it would go through the gypsum and then finish off through the inside air. So as you look at this construction, we're going to have, again, two different heat flow paths we're going to look at. One's going to go through the outside, siding, plywood, stud, gypsum, inside. And then the other heat flow is going to go through the outside, siding, plywood, insulation, gypsum, and inside. And then we're going to go ahead and take those two total resistances and go ahead and add it in parallel. So let's go ahead and I'll set up the table and maybe that might make things clear. So we have one heat path through the stud side, another heat path through the insulation side, and this is for the 2 by 4 construction. And then we're going to have also heat path through the stud side and heat path through the insulation side for the 2 by 6 construction. So let's go ahead and finish off our table. Just going to go ahead and draw lines here. Just give me a second to finish this. All right, so here's how it translates that we're going to have heat flow through the stud. It goes through the outside, siding, plywood, does not go through the insulation. Then it goes through the stud, gypsum, and outside and inside air. And then for the insulation side, it doesn't go through the stud side. So what we're going to do is add all this side on the stud side in series, add all the insulation side in series, and then add these two in parallel at the end. All right, so again, you guys can go ahead as a practice on your own, look up these numbers, but you'd be looking up the numbers the same way that we did in the prior example problem. So if I go through the stud side, I would have the insulation of the outside air to be 0.17. The resistance I was talking about, not the insulation, but the resistance value. 0.79 for the siding. 0.625 for the plywood. As far as how to get the insulation value for the studs, what you should do is go to table 5.1, and this would be in English units, so it'd be table 5.1a. And if you look on page 125 and you go to the bottom of table 5.1a, you go down and it says woods with 12% moisture content. You would go ahead and the studs would be made by softwood, so hemlock, fir, spruce, pine. And you see the conductivity value. The conductivity value should be between 0.74 and 0.90. Take the average of that and then use the thickness of a 2x4 stud. If you remember, a 2x4 stud is really 1.5 by 3.5. So if you take that thickness and you have the conductivity range to be 0.74 to 0.90, you take the average between the two, which would give you 0.82. You take that as your conductivity, you take this thickness, you do the math, and you would get a resistance, a thermal resistance of 4.26. And then again, finishing off the gypsum and the inside resistance, sorry, 0.45, then 0.68. Now, the outside would be for all these different construction scenarios, whether it's for the 2x4 stud or the 2x6 stud, whether it's going through the stud side or the insulation side, all these insulations are going to be the same. All these resistance values are going to be the same. As far as the stud is concerned, for the 2x6 construction, the resistance would increase, of course, because the thickness of a 2x6 is actually 5.5 inches. So this would give you a resistance of 6.71, right? Again, quantifying the thermal resistance as thickness over conductivity. You can go ahead and compute the resistance for the 2x4 stud to be 3.5 inches over 0.82, and you can compute the resistance of the 2x6 stud, again, using the same conductivity, but you would have a thickness of 5.5. So again, that would be the resistance for the 2x6 stud and the resistance for the 2x4 stud. As far as what the resistance is for the insulation, if you were to go to the bottom of page 122, you'll see that it gives you the conductances for various fibrous insulations. So if you look at the second entry for fibrous insulation, an approximate thickness of 3.5 inches, right? If you would have that for 3.5 inches, the conductance is 0.067. And since resistance is 1 over conductance, that would give you a resistance of 14.9, right? So for the 2x4 insulation, you would have a resistance of 14/9. And then for the insulation side of the 5.5 inch fibrous insulation, you have a conductance of 0.48, where the resistance would be the inverse of that, right? So in that case, it would be 1 over 0.048, which gives you 20.83. Hold on. A little bit of a typo here. I put 0.48. I meant to put 0.048. Right, so here I have 20.83. Right, so now that I have the thermal resistance of each of these individual constituents that make up the construction of the wall, I can go ahead and add them up. So for the stud side of the 2x4 wall, I have a resistance of about 6.98. On the insulation side, I have 17.7. For the 2x6 construction, I have 9.43 and 23.7. So now that I'm done, what I'm going to do is add these two numbers in parallel and add these two numbers in parallel. All right, I hope that makes sense to you guys. So let's go ahead and do that. Actually, just to make sure I'm explaining myself well, this is the method that we're using, right? So if I do this in terms of thermal resistances and I set up resistors, I have here heat flow going through the outside, then through siding, then through plywood, and then it splits across some of the heat going through the insulation and some of the heat going through the stud. And then it merges back to finish off through the gypsum board and the inside air. Now, I'm saying that this circuit is the same as this circuit. If I were to actually split this up, where I would have heat flow looking at things in series going through the outside, the siding, the plywood, the insulation, the gypsum board, and the inside. And then also parallel to that would be heat flow going through the same materials, but on the stud side. So it'd be outside, siding, plywood, stud, gypsum, inside. And then what I'll do is add these two in parallel to get my total resistance. These two circuits are equal, these two circuit designs. This is scenario 1, this is scenario 2. 1 and 2 give the same R total. All right. All right. So let's go ahead now and take what we came up with here, right? What we came up with here, total resistance in series going through the stud side of the 2x4 and the insulation of the 2x4 construction. We're going to take those two numbers and add them in parallel. And then we're going to do the same thing for the 2x6. Just to make sure we're on the same page in terms of how this lines up. If you were to look at the 2x6 or look at the stud construction, well, if I were to take a segment right here, this being a dimension of 16 inches separating the center of the studs, I should be able to use this as a sample area, right? For example, if I were to take this area here and then copy and paste it here, I would have, again, the same thing repeating itself, where I have 16-inch centers separating my studs. So what I'm going to do in order to compute the effective resistance is I need to take into account the area, right? Because the equation that we looked at earlier, this equation that we went over in an earlier video is valid for heat flow going through things in parallel, where the parallel paths that the heat flow goes through are going through materials of equal area, right? In this case, it's not equal area. In this case, you can see that there's going to be a greater area associated with the insulation than there is with the stud. So if I take this as a sample area, knowing that this, if I were to copy and paste it one after another across the wall, that this is the sample area that we will use in order to be able to figure out how much of the heat goes through the stud and how much of the heat goes through the insulation. All right, so coming back to this, I know that since the stud is 1.5 inches wide, 2 by 6 is actually, or 2 by 4 is actually 1.5 by 3.5. So this dimension here is 0.75 inches. So in that case, the area going through the stud is going to equal 14.5 square inches. Sorry, not through the stud, but through the insulation side. Right, so again, if I take this area, this sample area, I take a 1 inch high and 16-inch wide sample area, 14.5 square inches goes through the insulation, and 1.5 square inches goes through the stud. So if I'm going to quantify my resistance instead in terms of overall heat transfer coefficient, which is equal to 1 over the total resistance, I could quantify it this way. My total heat flow, in terms of total heat flow, looking at the portion of it that goes through the stud and the portion of it that goes through the insulation, I would basically quantify it by ratioing the overall heat transfer coefficients for the stud side and the insulation side and quantify that as on a per area basis. Right, so if I do, for example, the 2 by 4 inch construction, I would get my overall heat transfer coefficient is going to equal 1 over the total resistance on the stud side multiplied by a segment area plus 1 over the total resistance on the insulation side multiplied by a segment area divided by that total area. And that gives me 0.00, not point, I'm sorry, 0.064. And again, that's BTU per hour foot squared Fahrenheit. That same metric for the 2 by 6, again, 1 over the total area on the studs, on the total resistance on the stud side times the area plus 1 over total resistance on the insulation side times its area divided by the total area equals 0.048. So obviously there's more conductance on the 2 by 4 than there is on the 2 by 6. All right, I hope that makes sense. I know there could be some confusion as to where did this come from, right? Where did this designation come from in terms of finding the total conductance or resistance? Again, we got to think about it in terms of how we add up or how we find the effective resistance of heat flow going in parallel. This equation, again, works if you have heat flow being split into an equal flow area, right? So if I have these two things, for example, these two surfaces in parallel, and these two areas are not equal to each other, the flow is going to be split partly according to also not only the resistance, but it's also going to be split according to the area of each of those constituent pieces in parallel. So when looking at how to treat that, you get Q is equal to UA delta T. This Q, as it's going in parallel, is going to be split. This 2Q total is going to be split into the overall heat transfer coefficient of one side times area times delta T plus U2 A2 times delta T, where Q total is going to be the U total times area total times delta T. If you cross out the totals, right, what are you left with? You're left with U total times total area equals U1 times area 1 plus U2 times area 2. So then if you go ahead and solve for total area, for total U, you end up with the equation that we just used. Okay, so it's a way of calculating the effective either overall heat transfer coefficient or total resistance of heat flow in parallel when the areas at which the heat flow is seeing in the parallel flow is not the same. I hope that makes sense. I'm going to go ahead and stop this video at this point because this was a long example problem. We do have 2 more example problems to finish up for the chapter, and we'll do that in a fourth video. Thank you.